Hello, welcome to the channel of Namagiri Academy. This is the next lecture in the series of multiple integration, and in this lecture we shall see how to compute areas using double integration. So before we do that, let us recall how we defined double integrals. Now, the functions of uh, functions, how we defined the integrals of functions over regions. So when we actually are computing a real valued function over a, let's say, some region, let's take the example of a rectangle, just for the sake of simplicity. And suppose we have this function defined over this rectangle. Suppose it looks something like this. Suppose the graph looks like this. Okay, the diagram is not very accurate, but please understand it. Okay, this is the graph. This along the z-axis we plot the function values, and this rectangle is R over here. And we have seen that the double integral of this function, this f of xy, is a real number. This double integral actually gives us the volume of this solid that is formed by the solid that is bound below by this rectangle R, above by this graph of the function, and on the four sides by the wall that binds, the wall that connects the rectangle below and the graph of the function above. So this um, this the geometric interpretation of double integral is that its volume. Recall that in case of the integration of single variable function, the integral gives us the area under the curve, whereas in case of the in case of multiple integration, the double integral of a real valued function gives us the volume of the solid. Now here suppose we make a little change. Suppose we define this f of xy as constant 1. So here let me write this as over rectangle R, let's say. Suppose is constant function 1, then how does this change? This becomes integral of the constant function 1 over R, and that will be the volume of the solid that is formed by rectangle below the graph of the constant function above, and then the four walls. But what does this constant function look like? Now it will look like a cube. rectangular cube. Here we have our rectangle R, and now at every point we are plotting function f um, at a distance 1 from this region R, because our function is taking value 1 now uniformly. So it is something like this. Something like this. So now we are in fact getting a rectangular cube having R as its base and 1 as its height. Alright, fine. But what do we know about the volume of a rectangular cube? We know that the volume of a rectangular cube is, now I am not writing every detail over here, okay, since I am speaking, you know what I am trying to say, is the area of this base rectangle multiplied by the height. So area of the base rectangle R multiplied by the height. But height here is 1, so therefore this is area of R. Area of this base rectangle R. But here we have interpreted this V as the integral, double integral of constant function 1 over this rectangular region R. Now that gives us a formula for finding the area of the rectangle in terms of double integral. Now here you might ask, why do we really need the formula for area of rectangle in terms of double integral, since we can find out the area of rectangle just by multiplying its width with length. But it's not the question of a rectangle. This formula holds for every two-dimensional shape, and that is the power of it. If you replace this rectangle by a circle, even then this formula will work, and if you replace this by any random shape, thus this formula will work. And therefore this is very useful. And computing the double integral sometimes is much easier, rather iterated, since we have the device that is iterated integrals. We can comparatively easily compute this double integral, and therefore we can compute the area of any shape over here. So let us take one example. Let's say just to demonstrate the power of this method, let's say compute the area of the region bound between y equal to x square and y equal to square root of x. So we have seen this region earlier, so I will not explain much about how to draw this region. The region looks something like this. This is in the first quadrant. Y equal to x square is a curve of this sort, and y equal to square root of x is the curve of this sort, and they intersect exactly at this point, and the region at this point is 1, 1. This is the origin, and the region that is trapped between these two curves is precisely this. Now you can compute the area of this region using some other method. Okay, but if we have double integral at our disposal, here R is this region, then it becomes much simpler, because we know how to compute double integral of any function that is defined over this region, provided that the computing that provided that the function that we are defining over this region is not very complicated. Okay, here certainly it is not complicated, because the function is the simplest function, it's constant one function. Okay, so area of R in this case will be double integral over R dA. But how do we compute this, rather how would we determine the limits of integration for iterated integral for this region R? Here x is varying from 0 to 1, and y, for every x between 0 and 1, y will vary from 0, so y will vary from this lower curve to the upper curve. The lower curve is given by y equal to x square, and the upper curve is given by y equal to square root of x. So first we shall integrate with respect to y, and the limits are x square, and lower limit is x square, upper limit is square root of x. Now remember that our function is just a constant one function, dy dx, and the limits between which x varies are 0 and 1. Alright, good. So integral of 1 with respect to y is, so it is integral of dy, which is y. So y x square square root of x dx remains as it is, 0 to 1 square root of x minus x square dx. Now it is now we can as usual integrate this function in x with respect to x. Square root of x is x to the power half, it becomes x to the power 3 over 2 divided by 3 over 2, which is 2 over 3, minus x, the integral of x square is x cube over 3. and the um, limits of integration 0 1. So first substituting x equal to 1, we have 2 over 3 minus 1 over 3, and when we substitute 0, everything becomes 0, so therefore we don't have to worry about that. So this is 1 over 3. So that tells us, so now this will to some extent show you the power of double integral, because if now here you can see that we computed the area of this region quite easily, so to say. If you use some other method, then you may have to rather probably put put in some efforts to compute this area. So using this thing, using double integrals sometimes simplifies our problem a lot. So even some of the standard integrals can be computed using double integrals. Let's say compute the area of the standard ellipse given by the equation x square over a square plus y square over b square equal to 1. Now what does the ellipse look like? I am assuming that a is greater than b, so it's an oblong shape, and so it will be some sort of horizontally oblong. Okay, not a very nice diagram, but it's always difficult to draw a diagram using digital pen. Okay, so this is negative a and this is positive a, this is negative b, this is positive b. Alright, so we want to find out the area of this region. Okay, so as usual we shall call this region R, and we shall find out the double integral of function uniformly defined function 1 over this region R. Now how are we going to set the limit, determine the limits of integration? What does x vary between? X varies between negative a to positive a. Okay, so sorry, and what does y vary between? For every x, y varies from this point to this point. It is bound between these 2 points. This is the segment, so it varies. Okay, the length of the segment varies, so y is not varying from negative b to plus positive b for every x. Okay, you have to be careful about that. Okay, what is the value of what are the values of y between which it varies for every x. Let us solve that we can obtain using this equation. This is the same as y, if we subtract x square over a square from both sides, we get y square over b square equal to 1 minus x square over a square. And now if we multiply by b square on both sides, then this b square disappears, and then we can write y. Now if you take the square roots on both sides, then y will vary from negative b multiplied by square root of 1 minus x square over a square, and positive b multiplied by square root of 1 minus x square over a square. So these are the two values of y that we obtain, and y will vary between these two values. So negative b square root of 1 minus x square over a square multiplied by from negative to positive value, 1 minus x square a square. Now we have set the limits for both x as well as y. Function is uniformly defined and constant one. First we are integrating with respect to y, and then with respect to x. Right. So integral 1 multiplied by dy means integral of dy, which is y, but integral of dy means is y, so that is y all right. So substitute for y, so that is this minus of this, so 2 times b square root of 1 minus x square a square dx. Here we can equalize the denominator. We can write this as inside the square root sign. We can write this as a square minus x square divided by a square, and then this square root of a square can be taken outside, and it will become 2 times b over a, and inside square root sign we shall have only a square minus a square dx. Okay, now we can substitute if you know the ready formula for this, you can use it. I am using substitution x equal to let's say a sin u. So the dx will be a cos u du, and if we substitute, then we have to accordingly change the limits of integration. So when x is equal to negative a, we have negative a equal to a sin u, then that means sin u will be negative 1, and then it means u is negative pi by 2. So 2b over a. This is something that is, this we are now in the domain of integration of single variables. So I hope you know this. And when x is a, if we substitute x equal to a, then we get sin u is equal to 1, but sin u is equal to 1 means u is equal to pi over 2. So when x is varying from negative a to positive a, u will vary from negative pi over 2 to pi over 2. And now we can substitute square root of a square minus a square sin square u, and dx is a cos u du. Alright, so 2 times b a integral negative pi over 2 to pi over 2 a cos square u du. I think this a and this a will combine together to give us a square, and this will become 2 times we can, if we take out this constant a outside the integral sign, to be 2ab negative of pi over 2 to pi over 2 1 plus. Now this cos square u, we need to integrate cos square of u, which can be integrated using our usual formulas. 1 plus cos of 2u divided by 2b, and then that becomes now just a routine thing. 1 over 2 is it is u over 2 plus sine of 2u divided by 2, and then multiplied by 2 is 4, negative pi over 2 to pi over 2. Now when we substitute pi over 2 for u in this sine term, it becomes sine of 2 times pi over 2, which is sine of pi, which becomes 0, and similarly here it becomes sine of negative of pi, also that becomes 0. So sine plays sine doesn't have any effect on this whole term, or this quantity, final quantity that we are going to compute. 2 times ab, only this u over 2 will show some effect. So pi over 2 divided by 2 is pi over 4 minus pi over 4, so plus pi over 4. So pi over 2 cancels out, so and this becomes pi ab. So that matches with, we know that the area of the standard ellipse that is given by this formula is pi ab, and we have actually computed it using double integrals. So that matches with our intuition and our prior knowledge. So that uh, completes our discussion on the computation of areas using double integrals. So I will stop here and let us meet in the next video.